Welcome and good afternoon. This live interactive session for NPTEL course Transition Metal Organometallic Chemistry Principles to Application. So, as all of you know that we have completed 10th week question answer session in last Tuesday, but from the starting of this session this live session was behind of this week content. That is, live session was 1 week late from this week content which is released in the portal. As our exam is nearby and I thought to take an extra class on the last 12th week, that is on October 15. That day I will discuss no other questions, but within 1 hour or 1.5 hours I will totally cover a rapid summarization of this course. So today and the next Tuesday, that is upcoming Tuesday, that is 8th of October, I will finish this live interactive problem solving session so that I will have one more week for summarizing the course content through the slides and pointing out the important topics which can be asked in the final examination. That's why today I will complete the week 11 content through this problem solving session. I will wait for another 2-3 minutes, though it is an extra class. That's why I will wait for 2-3 minutes. If anybody joins, then I will start discussing the session. So this session, today is Sunday, so you will get the recording of this session on YouTube after tomorrow. So our as usual session as Tuesday from 6 to 8 pm will be continued in last 2 weeks, that is October 8 and October 15. So October 8 I will discuss the question answers of week 12, and then October 15 I will discuss the summary, that is the overall course content in a rapid mode. So in the last day I will not discuss any other question because in this 12 live interaction I have covered more than 140 questions. Every day I discussed 13-14 questions, so that will be more than around 150 questions. So 150 questions from my session, and in the portal you already have 120 questions, that is each week have 10 questions. So that is more than around 300 questions you got from this course, which I believe is enough to get your concept clear and understand the course very well. So for that I will wait for another 2-3 minutes to join if anybody joins. Then I will start discussing the today's session. Okay. As we have seen that in week 11, from our transition metal carbonyl halide to move to transition metal olefin complexes. So in this week we have seen how transition metal olefin complexes has been prepared, what is their bonding orbital, how they are oriented, and which orbital of the metal are interacting with them. So we have discussed two different types of. One is the conjugated olefin. So olefin can be two types. One is the conjugated olefin, another can be the non-conjugated or isolated olefins. That is called the diolefins. So before moving to the diolefin, we have completed our discussion with olefins system in this week. So there are several methods for the preparation of transition metal olefin complexes. So JSS salt is one of the very good or well known example for these transition metal olefin complexes, having the formula KPtCl3C2H4. In JSS salt, this olefin bounded to the platinum in eta 2 fashion. So the reactivity depends on the ligand, that is olefin to metal sigma donation, and then metal to olefin pi back donation. There are several methods available for the preparation of this olefin, and these metal olefin complexes are very good source of metal precursor in their low valent oxidation state to synthesize different other metal complexes, as well as is involved in the catalysis. So without wasting further time, I will directly move to the question answer session of this week, that is the week 11. And after this 11 week, I have 11 questions. So after 11 questions, I will discuss the conjugated olefins, that is the the conjugated olefin, the butadiene system, which is called diolefin, that is the two olefinic double bond as a conjugated system. And I will discuss their molecular orbitals, as well as which molecular orbitals of olefin interact which molecular orbital of the metals, and then how their energy is distributed, what is the homo lumo, like that. So first I will discuss the 11 questions from this olefin system which has been dictated in this week 11 series. So welcome again to this live interactive problem solving session for the NPTEL course Transition Metal Organometallic Chemistry Principles to Application. So today our first question is, the in metallocyclopropane complex the CC sigma bond is weakened by. So you may think that how we are moved to olefin to cyclopropane, metallocyclopropane. So that thing I will discuss in the later on with the help of this question. So first question says, in the metallocyclopropane complex the CC bond is weakened by. We have option A, that is the attraction between the substituents on the metal cyclopropane ring. Option B, ligand to metal sigma donation, and option C, metal to ligand pi back donation, and option D, the absence of agostic interaction. Our question is how metal cyclopropane complex the CC bond weakened. Now the question came how this metal cyclopropane is formed. So with that we can say that we have this. So we are discussing transition metal olefin complexes. So transition metal is bound to an olefin. So when this transition metal bound to olefin is happens in two ways. So the olefin has pi orbital as well as pi star orbital. So here pi is filled and pi star is vacant. So pi is filled and pi star is vacant. So this pi bond is when donated to the metal center. So this will form a coordinate bond to the transition metal, that is olefin to transition metal sigma donation, whereas transition metal donates its electron to this vacant pi star orbital, that is called a transition metal to olefin pi back donation. So when the sigma donation is more, that means the electron density on the pi star from bonding orbital is donated to the transition metal. That's why the bond of this CC, this is C and this is C. So this CC bond, as the pi electron cloud from in between these two CC bond is donated to the transition metal and in a sigma manner. So this bond will this bond order will decrease because of donation of electron cloud to the transition metal. Whereas when we have the transition metal which donate electron to this pi star, then pi star will be populated. So as we know that the population of pi star will also decrease the CC bond order. So here, as donation of this pi and acceptance of the pi star causes the decrease of this CC bond. That's why we can say that the ligand to metal pi donation and metal to ligand to metal pi donation and metal to ligand sigma ligand to metal, that is the ligand to metal sigma donation and metal to ligand pi back donation, both weakens the CC bond. So metal cyclopropane is generally is metal, whereas this C and C, this is called the metal cyclopropane. So here you can see that if the sigma donation is predominant, so here this bond will be have an ether 2 mode of fashion. If the pi donation is predominant, that is the transition metal donates very much electron to this pi star orbital, then pi star orbital will be more populated. So as we know that the pi star populated, the CC bond order decreases, and then because of this decrease is so much that olefinic character of this CC double bond will be lost, and then the instead of sp2 hybridized, this will be sp3 hybridized and form a metal cyclopropane ring. Metal cyclopropane ring is basically called when a metal is introduced in a cyclic three-member ring system, while other two are carbon. This is called the metallocyclopropane ring. Okay. With this, I want to go with the next question. I think this question is clear. The next few question, or next all of the question is now will be based on the preparative procedure of these metal olefin complexes and mm, some of the properties of this olefin. Next question says that pairing the product of the reaction. So we have our reactant iridium ClCO PPH3 whole twice. It is reacting with the and olefin R2C Cr2. So this is a very general reaction for formation again in the all of the complexes. We can say that as we are discussing the metal olefin complexes, so like the previous, or we can say that the option elimination can be one of the way to answer this question, but for the final examination when everything is combined, so that time it may be difficult to answer this question with option elimination. But here we can see that we in is the so our target is to formation of metal olefin. So here we have seen only the two complex have metal bound olefin structure, that is option number A and option number D. So this is called the metallocyclopropane, and this is not the ether 2 bonding mode or olefin bonding mode. This is the metal alkynyl complex. So this is not the olefin bonding or cyclopropane bonding mode. So B, option B and option C is cannot be our correct answer. So in between option um, A and D, so this question is very interesting. This question we say it as the addition of this olefin to a transition metal complex. So here, so when we have these types of iridium, so here we can see that only chloride is in minus oxidation gives the, so iridium here is plus 1 oxidation state. So here when this will add to this, this will add to this, that is CH2C double bond Cr2 to get double bond Cr2 to get our desired transition metal olefin complexes. So our correct answer will be option number A, not option number D, because the removal of PPH3 ligand from this late transition metal is really difficult, or in normal condition it will not remove. So here one interesting thing we can see that here iridium ClCO PPH3 whole 2 is no, there is no leaving group or no group is leaving when this alkyl moiety or this olefin is bounded to the metal. Also here we can see that iridium center is remains in plus 1 oxidation state. So this is called this is looks like a oxidative addition reaction, but here we need to know that the oxidation doesn't happen to the metal center. So here the electron only, the total electron count, that is this iridium, cobalt, rhodium, iridium. So cobalt is D7, so D9 plus chloride 1 plus CO2 plus PPH3 4. So total this is 16 electron system. Now 9 plus 1 10, 11 12, 12 plus 4 16. So here this iridium complexes, that is our option, iridium complexes, that is answer, that is we will be adding up another 2 electron to give 18 valence electron complex. So this is 18 valence electron complex. So because this is undergoing the addition of one ligand, but we need to take a note of this reaction that our metal center doesn't get oxidized. So this is addition but not the oxidation of the metal center. Metal center remains in +1 oxidation state. So option A will be right answer for this question. Another question which is very important question, then preparation of this diolefin complexes. So this method is called another method of preparation of transition metal olefin complexes. So here we have nickel chloride and trialkyl aluminium and a 1,3-butadiene. This 1,3-butadiene is mainly a diolefin. This 1,3-butadiene, this is the cis form, and as we have written, this is the trans form. So in presence of this butadiene and trialkyl aluminium, this nickel center, that is the nickel salt, undergo reduction to form a very interesting complex, that is nickel in +2 state, it undergo nickel in 0 oxidation state, and it form a option number B, which is cis orientation of this, and nickel is in nickel 0 oxidation state. So this is this reaction is very much important and interesting reaction for the preparation of olefin, transition metal olefin complexes. So this question is also a very good question for this series. So the next question or fourth question of this today's discussion, the further modification of these nickel complexes. So when this nickel complex is reacting with CH812, what will be the product? So here this is C8H8, that is, it is written as is called cyclooctadiene. If we calculate this 1, 2, 3, 4, 5 cycloocta, we can write 1, 5 diene. So when we look at this is called the COD, cord as a ligand. So cord is also a very good or a powerful source for this ligand system. So this will react with this nickel complex to get the dicord nickel 0 complex. So this is generally represented as NiCOD whole 2. So option C will be our right answer. So here also, like the previous, this also nickel 2 in 0 oxidation state. So this, why this reaction is important? Because in this reaction the nickel cord 2 complexes act as a nickel precursor as or as a source of nickel 0. This is very important in the transition metal organometallic chemistry to form as well as the metal precursor. So these act as a metal precursor for different transition metal organic compound synthesis. So another application when this nickel complex is reacting with ethylene molecule, simple, what will be the product? So here this an interesting product from in this reaction. Here our right answer for this reaction will be simple product of option number D. So here the olefin, which is more stronger ligand compared to this, which will replace this ligand system and also stabilize the nickel G nickel in nickel 0 oxidation state, but the stability of this is less compared to that previous one, but in certain condition this olefin will also form the nickel in 0 oxidation state. So here option D will be the correct answer. Next question is which is similar like the previous one. Here we have cod, 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 platinum dichloride. The structure is the same like this, and it is platinum Cl. Cl. This is the structure of quad PtCl2. So when it react in this reaction, it will also give the same product like the previous we got. So here also that is the ethylene molecule in excess, or it is ethylene atmosphere. So our product will be the same like the option number C, like for the nickel we got. So this complex is somehow more stable compared to the nickel. So here we will have the this 3 Pt C2H4 whole thrice. This will be have our desired product from this reaction. Our next will be again that method which we discussed earlier. We have like the nickel chloride and trialkyl aluminium. Here the same, that is the preparation of transition metal olefin complex. So here is the another interesting method for transition metal olefin complexes. So in this we have zirconium salt. So here you can easily see that zirconium in plus 4 oxidation state, and we are using sodium in mercury, that is sodium amalgam. This sodium amalgam will be used as the reducing agent. So this will reduce this zirconium, and then it will react with C7H8 to form the transition metal olefin complexes of zirconium with or in zero oxidation state. So here in this question, one thing to notice that, or in this reaction, one thing to notice that when we have a strong reducing agent like NaHg, this is a reducing agent. Reducing agent. Reducing agent. So this reducing agent will never keep this metal center or metal salt, metal chloride in positive oxidation state. This will always reduce the metal. So here in all the options you can see that in plus 2 or in plus 2 oxidation state metal. So our answer for this question will be obviously the option number B, where metal is in zero oxidation state and bonding mode is neutral olefin. So here option number B will be correct answer for this question. So this will be the correct answer for this question. The next question is, the reaction of ruthenium trichloride in ethanol in presence of rhodium trichloride, not ruthenium, rhodium trichloride in presence of ethanol water. So this reaction also, if we have a formation of olefin, so we have seen another reaction which is resembles to this reaction if we have ruthenium RuCl3 dot H2O or ruthenium trichloride hydrated salt. If we react with this alpha phenandrine, structure is like this. In ethanol, what will be the product? This is also a question of this type, but the product, so for the rhodium, when we have the alkene, that is ethylene, and for the ruthenium also we will have an cycloalkene, that is another unsaturated ring. But the formation of product is slightly different, but one thing is common in both the mechanism. So this question is very interesting and very important in making the metal precursors. I am always saying metal precursors. These precursors, why they are important? Because when we are synthesizing the organometallic compound in different methods, these metal precursors which are stable enough are called metal precursor because these are stable enough. Also, this contains a labile group which can be replaced by our designed ligand system. So when we are making our ligands, that is the complexes, ligands can be organic metallic compound or it can be any other nitrogen or phosphorus donating ligand, that is the coordination compound. So these metals precursors, which I am saying precursor, is a very good source for getting that complexes. So if we want the nickel, like the last example, to be in zero oxidation state, so we can readily use the available precursor to have this in zero oxidation state to in our complex. If it is can stabilize the nickel in or platinum in zero oxidation state, so it will directly have the metal in zero oxidation state. So that's why these precursors of metal precursors are really important during the complex, that is the coordination chemistry, that is the formation of coordination compound, as well as the when the ligand system contain one carbon donating site to form as a organometallic compound. So with this, the answer of this question will lead to the another rhodium metal precursor, that is the rhodium 1 electron reduction will be happen here. So option A will be right answer for this question. So you can easily see that rhodium here in plus 3 oxidation state. Here simply the rhodium in plus 1 oxidation state. That is the oxidation state have been decreases, which indicates that the reduction happen with the help of this system in it. The what will be the answer for this question? So this reaction also happen in ethanol refluxing condition. To give another important ruthenium precursor, so this will give, so if you have Ru ruthenium Cl3 dot XH2O, because this ruthenium salt is commonly or cheaper available version is ruthenium chloride hydrated, which will react with this alpha beta unsaturated compound, this is alpha phenandrine, and then in ethanol reflux ETO is solvent reflux. So here this solvent plays an important role to perform this reduction. So this will give rise to ruthenium complex, which is ruthenium, and then this ring undergo the aromatization. So how it will undergo? This will convert to these two hydrogen will remove to give this ring as an aromatic Simon ring. So this is as substituted in para position. This is called the para-Simon ring. So ruthenium para CYM Sim dichloride Cl2, and this will form a dimer. So it will write like this way. So this will be the product of this reaction. So what will be the structure? It's a ruthenium. We have Cl, ruthenium, Cl, now this side will be one Simon ring. So this can be drawn like this way. And Cl, and this side will be another Simon ring with one Cl. So here interesting thing to note that ruthenium is plus 2 oxidation state. So and here where we have started ruthenium trichloride, where ruthenium is plus 3 oxidation state. So we can see that in ethanol medium the reduction of ruthenium center happens, and this alpha phenol moiety converted to the Simon ring by this aromatization process. This is a similar type example of this, that's why I discussed here. Another question is again the potassium C2H4 minus 20 degree. What will be the product for this reaction? So here in presence of potassium metal, this metal center also undergo the reduction, one electron reduction, to give cobalt 2 to cobalt 1 salt. So this is another source of cobalt 1, because this CP ring is minus 1 and this olefin is neutral. So here our answer will be option number B. So these reactions are not understandable. So this reaction is a preparation of different metal olefin complexes. So we have our olefin bounded to a very interesting cobalt complex. So here option B will be right answer. Then the last question of today's discussion is the MnCl2 in C6H4 Mg 2 dot THF PME3 and in presence of C4H6 environment THF at 0 degree centigrade. So this reaction you also can find out the olefin moiety which is attached to this magnesium. Here the olefin is again the 1,3-butadiene, that is here 1,3-butadiene C4H6. This moiety. So as we have seen earlier, this moiety is performed as very good ligand to form transition metal olefin complexes. So this, and also it is attached to the magnesium, that means this molecule bears a reactive center. Now in presence of manganese chloride, the C4H4 moiety it eventually transfer to this manganese chloride, and this center will also undergo the reduction as the previous one to form our desired complex, which is complex number D. So two of these eta 2 bound olefin and one vacant site will be occupied by PME3 ligand. So this will another have the manganese complex. So this option number D will be our right answer. With this I completed the 10 question, which question most of the question are reaction type question, because these reactions are very much important in terms of their synthesis of transition metal olefin complexes. With this I move to our last question of today's discussion question answer series, that CC, stretching frequency. So here the stretching frequency means this is IR stretching frequency. So stretching frequency means, or you can write here nu CO. So we can write nu C double bond C, also indicate the CC stretching frequency in IR. In the free ethylene moiety is, this question is also another very important question. And most important thing is how this stretching frequency changes when this ethylene molecule is bounded to the, or ethylene molecule bounded to the metal. So So in the free ethylene molecule, the CC stretching frequency will be unaffected by any other external substitution or coordination. So it will be highest, that is 1623 centimeter, and here all the unit is important, that is 1623 centimeter inverse. So the unit is very important. So is centimeter inverse. Okay, so 1623 centimeter inverse will be the stretching frequency of. Now the question is how this stretching frequency changes when it is binding to the metal. So as we say earlier that when we have metal bound as eta 2 mode, that is first is the sigma donation from pi star, that is uh, uh, metal olefin, that is sigma donation, and then metal 2 olefin is pi donation. So this donates electron from pi and this accepts electron from pi star. So in both the cases the sigma donation decreases and also the pi star electronic contribution increases in transition metal olefin complexes. So that's why in this manner the CC bond, as I discussed in the first question, that is this CC bond is weakened by, so this back donation decreases the CC bond. As CC bond strength decreases, obviously the stretching frequency will be decreases, because the IR stretching frequency only depends on the CC bond strength, that is, or the bond order of CC, carbon carbon bond. So take an example for this. So we all know the Zeiss salt, ZEI. Zeiss salt is olefin metal transition metal fast transition metal olefin complex, which is discussed in more detail and their bonding. So the structure of it is PT, Cl, Cl, Cl and CH2. Overall charge is minus with K plus. So here in this CH, this CC stretching frequency is around around 1243 centimeter inverse. So this is a very important. So here we can see that upon binding to this metal center, the CC stretching frequency subsequently decreases from the free ethylene molecule. This thing we need to know. So free is 1623 centimeter inverse. When it is binding to the metal, it will be always decrease because of that sigma donation as well as pi back donation. Now I have discussed all this question answer series, and at the end of this today's discussion or today's lecture series, we move to another transition metal olefin complexes, which is transition metal diolefin. So that is transition metal diolefins. So here the transition metal diolefin means diolefin is this. So this is 1,3-diene. So this is 1,3-diene, 1,3-butadiene. This is conjugated, and diolefin can also be non-conjugated, like so these two double bond, this is 1 2 3 4 5 and 1 2 3 4. See, this is 1,4-diene. So this is non-conjugated. Okay. So now we are going to discuss the energy and bonding orbitals of 1,3-butadiene. So 1,3-butadiene have 4 carbon atom. So the 4 carbon atom means it will form 4 molecular orbital. So first, so that is psi 1, psi 2, psi 3 and psi 4. And as we know that the value of psi increases, the energy of the orbital also increases. So the energy order will be psi 1, psi 2, psi 3, that is energy increases. So now we want also, if we calculate the node, so psi 1 have 0 node, psi 2 have 1 node, psi 3 have 2 node and psi 4 have 3 node. So that is, if we have psi n orbital, so number of node will be n minus 1. So this is the rule of thumb. Okay. So what is the definition of node? Node means, in simple word we can say, the node does not contain any electron density, that is the 0 electron density. So in the node we don't have any electron density. Okay, now we move to the diagram of this. So how it will be look like this? Let's say we have psi 1. As I say, psi 1 will be lowest energy, that's why this will be our order of energy. So psi 1 we can write like this. So these are the lobes, or so psi 1 have node 0. That means all the orbital are on the same phase. Now which metal orbital have the same phase? So this can be metal s orbital, metal px orbital, and d z square orbital. So these three orbital of metal can form a bond, and this bond is generally called the sigma bond. Now we can draw the psi 2, that is having one node, and this node will be here. So here we have this, and this. So here node equal to 1. So which metal orbital can interact with this? Simple, if this is py orbital, let's say like this, py, or this can be like this way, py, this lobe will interact this, and this phase will interact this. Okay, and then metal orbital, which will be, so this can be metal dYz orbital. So these orbital are from the pi bond, because these types of interaction are pi type of interaction. Another is, this is psi 2, and then we have the psi 3. Here number of node equals to 2, and have the two nodes, and two nodes will be here and here. So this will be like this, and this. So which orbital can form interact? So again the same. So this can be made p, if p z orbital. So how that pz orbital will be oriented? The orientation will be like this. So here in the below phase we have this, and this will be vacant. This is pz. And how dz orbital and the d orbital will be dxz. So dxz orbital will be like this, it will be like this. So here these two phase will be same phase, and fourth one is does not have any lobe. So this will be 3 lobe. and all are in opposite direction. So this can be node equal to 3 and only dxy orbital can interact this. So this will node 1, that is the psi 1 from the sigma bond, psi 2 and psi 3 from the pi bond, and this psi 4 will form the delta bond with dxy orbital. So the energy and the phase of this orbital in butadiene system and how it is interacting with the metal, I think is clear. So in the week 12, that is the last week, which I am going to discuss the day after tomorrow, that is week 8th October, which will be the end of this live discussion session, and in the last day, that is the 15th October, I will overall summarize this week content. I hope this is clear, and this will give you a clear idea of this week. If you have any doubt, you can ask me in that comment section of the YouTube, or also directly ask me in the live session from this session every Tuesday. Only 2 Tuesday left, so 8th October and 15th October from 6 to 8 p.m. Today's session I took extra to finish the week content or problem solving content within the time, so that there is enough time left for the exam. So in the last, so in the by the 8th October I will finish the week 12 content, and then that is the 15th October I will summarize the overall course. Overall course in a very rapid fire process, so that you will get an overall idea which question, which topic is most important in exam point of view, and which reaction you need to remember when you are going for the exam. I hope this is clear, and thank you for watching this session. I will upload the questions. I will upload these questions in the drive, and also I will share the recorded list of this session on the YouTube. You can watch there. If you like this, you may join in the next session, that is next interactive session. Today's was an extra session to complete everything within time, and also complete my ticket responsibility with this in this course. So next Tuesday, that is 8th October, I will 8th October I will discuss the last week content, that is the week 12 content, and then I will discuss that summary of this course in last day, that is the 15th October. For that time, if you have any question, you can ask me in the remaining 2 Tuesday, and you can also, if you have, I hope this 120 question, there is more than 120, around 150 question from my this interaction session will be helpful for solving your questions in the exam, also for better understanding the course. So in the exam there will be two types of core question. One is the MCQ, one is the MSQ, and I think there will be different section for this question. So when you are answering the MSQ or MCQ question, my suggestion is always read. If you find your correct answer in first option, second option, don't stop reading the options, because sometimes there is the possibility of getting two options correct in the question. Then if it is a MCQ, you only need to choose the most appropriate option of that series or of that question. So please read all the 4 options in the exam, and I hope this session question will be also helpful, and the question will be based on this session. And today's session also will be, I think, helpful for solving your assignment problems in the portal. If you have any doubt, please ask me in the next session, or you can also post it in the YouTube comment box. Thank you for watching from the YouTube, or as nobody joined the student session, so that's why I am closing this session for now. Hope to see you again in the next session, next two session, with more interesting questions, with uh, more elaborate explanation to that. Till now, thank you and bye bye.